Hello, welcome. In the last section, we talked about the dot product of two vectors, and we saw some applications of dot product. In this section, we're going to talk about the cross product of two vectors. Let's suppose we have two vectors, A with components A1, A2, A3. We have another vector B with components B1, B2, B3. These two vectors determine a plane. For example, we have a vector A, we have a vector B, and these two vectors determine a plane as shown in this figure. We want to find a vector which is perpendicular to both A and B. So the vector must be perpendicular to the plane here. Now we see that there are two possible vectors, at least. One in this direction, the other one in this direction. So let's try to find the component of these vectors C. Suppose the vector C has component C1, C2, C3. So the vector C must satisfy these two equations. Since the vector C is perpendicular to the vector A, it must satisfy this equation. A dot C must be equal to the scalar 0. Similarly, since the vector is perpendicular to the vector B, it should also satisfy this equation. B dot C equal scalar 0. To obtain the components of this vector C, we need to solve these two equations. So when we write the equations in component form, the first equation gives this: A1 C1 plus A2 C2 equal A3 C3 equals 0. And the second equation gives this: B1 C1 plus B2 C2 plus B3 C3 equals 0. So we have two equations in three unknowns, namely C1, C2, and C3. We have fewer equations than the number of unknowns. In linear algebra, this is known as an underdetermined system. Let's try to solve this system by eliminating the C3 from these two equations. To eliminate C3 from these two equations, we need to multiply the first equation by B3, this coefficient, and the second equation by the negative of A3. So we get these two equations. Observe that if we add these two equations, we can eliminate C3. So now adding these two equations, we have this equation. Now this is an equation of type 2p plus 3q equals 0. We're considering this as p and this as q, where, for example, this is 2 and this is 3. So this is a single equation in two unknowns. There are infinitely many possible solutions. For example, I can set p equals 3 and q equals -2. You see, becomes 6 minus 6, which is equals to 0. So this is one possible solution. The other possible solution could be p equals -3, q equals +2. This once again gives -6 plus 6, which is also 0. We can set the values of p and q in infinitely many possible ways. Let's pick the value of c1 as this coefficient and the value of c2 as the negative of this coefficient, just like the case 1 here. So we have two components of the vector c known. To get the third component, c3, we can use this equation. So we are going to put the value of c1 and c2 into one of these two equations. Let's substitute in the first equation. So this is a1 c1 plus a2 c2 plus a3 c3 equals 0 after the substitution of the values of c1 and c2. Now if we multiply the terms by a1 here and a2 here, we get these four terms, and where we see there is a simple cancellation. So keeping the a3 c3 in the left hand side and transpose the other two terms to the right hand side, and by making a factor of a3 we get this equation. Since a3 is not in general always 0, we can divide the equation by a3. So we're left with c3 as a1b2 minus a2b1. So therefore we get the component of the vector c. This is c1, this is c2, and this is c3. Now we might think we had two such possible options for c. We had two options for c, this one and that one over the plane. So which one have we obtained by this definition? So let's calculate the vector orthogonal to the unit basis vector in the positive x direction and the unit vector in the positive y direction. So we are calculating the vector c, which is orthogonal to the vector I and j. So by applying the formula, we get this vector with components 0, 0, and 1. So we have the vector k. And this is very clearly, and this is shown here. So we have a vector I, we have a vector j, and by applying this definition, we obtained the vector k. So this simply followed the right-handed rule. The right-hand rule. Therefore, we will pick this definition as the definition of cross product of two vectors. Definition. If A is a vector with components A1, A2, A3, and B is a vector with components B1, B2, and B3, then the cross product of A and B is the vector is denoted by A cross B, whose components are defined by this formula. So instead of C, now we will write A cross B, and this is, we notice this is the C1, and this is the C2, and this is the C3 component, the vector C. This vector A cross B is written in terms of the angular brackets. In terms of the standard basis vectors, we can also write this in this way. Here, notice in the first component, we don't see the appearance of any A1 or B1 components. It is just a combination of the second and third components of the vectors of A and B. So A2, B3 minus A3, B2. Now, if we cyclically permute the indices in this direction, 1 would be changed to 2, 2 would be changed to 3, and 3 would be changed to 1. Then we can obtain the second and third components of the vector A cross B. For example, A2 would simply become A3, B3 would become simply B1, and A3 would become A1, and B2 would become B3. And from here, A3 would become A1, B1 would become B2, A1 would become A2, and B3 would become B1. Just a simple cyclic permutation of indices. In terms of determinant, we can also write the components of the vectors A cross B in this particular form. If you remember, the determinant of a matrix A1, A2, A3, B2, B3 equals A2, B3 minus A3, B2, which is just the first component. So the first component can be written in terms of a determinant or by using two bars. So we have a change in the sign to put the quantity, the second component, in the right form of the determinant. So these three determinants, 2 by 2 determinants, can be put into a 3 by 3 determinant. So this is an alternative formula or definition cross product. This is often helpful in memorizing the formula. Notice in the first row we have the standard basis vectors. The standard basis vectors I, J, K. In the second, we have the components of the first vector A, and in the third row we have the components of the second vector in the cross product. Let's calculate the cross product of the vectors A and B with components as shown. Just by using the formula above, we can calculate A cross B as the formula shown in the determinant. So first row contains the basis vectors. The second row contains the components of the vector A, is 2, 3, and 0. And the third row contains the components of the vector B, which are 1, 0, and 5. So we have like this. So it's 3 times 5, 15, minus 0 times 0. And we have second component, 2 times 5 minus 0 times 1. And then for the kth component, we have 2 times 0 minus 1 times 3. Which is 15i minus 10j plus 6k. We can also write this in terms of angular brackets. 15, comma, negative 10, comma, positive 6. Let's see another example. In this example, we want to show that the cross product of a vector with itself is a zero vector. And this is true for every 3 vectors. A vector with 3 components. Let's try to prove it. Suppose A is a vector with components A sub 1, A sub 2, and A sub 3. By definition, A cross A would be determinant whose first row contains the standard basis vectors, and the second and third rows contain the components of the vector A. In this case, they are both same. So if you expand, for example, the first component would be A2, A3 minus A3, A2. Similarly, the jth component would be A1, A3 minus A3, A1 plus the kth component would be A1, A2 minus A2, A1, which is 0i minus 0j plus 0k, which is none other than the zero vector. End of the proof.